So, in a previous video, I demonstrated that fossils are not evidence for evolution, because the picture that they paint of a smooth, goal-directed transition from one organism to the next does not fit the theory itself, which has no teleology or end goal or design inherent in it. I use search algorithms as an analogy for why evolution should proceed in a random and chaotic frenzy, leaving behind monstrosities in the fossil record, rather than the neat and idealized organisms that we do have evidence for. Check the link in the description if you haven't seen it yet. Now, some intrepid evolution respecters in my comments pointed out that search algorithms aren't a good demonstration of evolution, and that I should have used genetic algorithms instead. But there was a reason I chose search algorithms, and it was to demonstrate a point about what kind of searching evolution needs to do. But I already said my piece in that video. Instead, what I want to talk about in this video is genetic algorithms and why they not only do not demonstrate evolution, but why they count as evidence against evolution. But how can algorithms inspired by evolution count as evidence against evolution? Well, I'll talk about just 3 of the issues that genetic algorithms expose, which are still unresolved issues for evolution. Issues which not only cast doubt on evolution in theory, but as I'll show are backed up by experiment and so count as strong disconfirming evidence of the theory. These issues are teleology, convergence, and open-ended evolution. First, very briefly, what is a genetic algorithm? Well, these are computer algorithms inspired by the theory of evolution, and they're used to optimize systems in ways that human engineers can't. For instance, pictured here is an antenna created by a genetic algorithm, which is even more efficient than antennas that humans have engineered intentionally. So these might seem like a solid model and demonstration that evolution is true, right? Well, not really. Let's take a deeper dive into the 3 issues. First big issue is teleology, associated with intentionality, and it's a key component of genetic algorithms. One of the ways that these algorithms are capable of optimizing a system is that they require intentional information front-loading by an intelligent agent. For instance, if you use a genetic algorithm to design a bridge, you'll likely provide a basic bridge design to the algorithm, and the algorithm will use that as a springboard to create a more optimal design. You also are going to provide the parameters that need to be tweaked, so you might assign computer bits to certain features like tension or angle. And then as the algorithm tweaks these bits, you provide a large swath of computer code that translates these bits into changes to the bridge design. Notably, the algorithm isn't writing this information itself, it's merely guiding or directing the information you've already written in order to optimize it. Similarly, you have to provide a goal, or what's called a fitness function, which evaluates how well some permutation of information conforms to an intended purpose. This is called a heuristic, and this is why I used the example of search algorithms, because without this heuristic or end goal in mind, searching a space for an optimal solution is extremely inefficient, if not impossible. And guess what? Evolution does not have heuristics or end goals. There's no divine mind directing evolution and telling creatures, you become this, and you need wings, and you need fins. That's teleology, or design, or intention. And if you say those things are involved in the creation of life, then evolutionists will be quick to label you a creationist because it isn't part of the theory. But these sorts of goals are exactly what the fitness function is telling the algorithm. The reason the algorithm doesn't just aimlessly wander around finding pointless designs is because it's tightly constrained to an end goal. Now you might be tempted to say that selection, natural selection, can act as a fitness function, but it can't, because selection just means something didn't die. So on the one hand, a fitness function is static and it's specific, something like strong bridge stability, versus selection, which is non-specific and constantly in flux. So unless you want to say that there was an intelligent designer who infused creation with information and then guided evolution with specific goals in mind, then genetic algorithms are not going to be any help to you on this front. The second issue is convergence, and the theory isn't going to fare any better here either. Convergence is the idea that when optimizing towards a goal, 2 things will tend to happen. 1, you will tend to get stuck on local optimums before you find the global optimum, and 2, as you approach an optimum, the population being evolved will become homogeneous and innovation will cease. So very briefly, let me explain what a local and global optimum is. If you were to graph how optimal a system being created by a genetic algorithm is, you'd see something like what's in the background. A function with a lot of peaks and valleys and one or more highest peaks called a global optimum. The lower peaks might be called a local optimum. The problem genetic algorithms run into, and this will be very relevant to evolution, as you'll see in a moment, is the genetic algorithms tend to get stuck on local optima. Once it finds a solution that's better than all nearby solutions, it won't want to change because, well, all other solutions will score lower per the fitness function. But what we really want to find with the algorithm is the highest reasonable optimum, which is sometimes referred to as the global optimum, since it's higher than all other alternatives, or at least not lower than any others. So in order to avoid getting stuck on a solution that's good enough, but not as good as it could be, genetic algorithms will often introduce rapid mutation into the system to kick the algorithm out of a local optimum and have it try other solutions. The problem is, evolution can't do this, because too much mutation too quickly is typically lethal to an organism. I wonder if we've ever done experiments that confirm that this problem of convergence applies to evolution in practice.
So what was the earliest sort of big findings from the experiment?
The first thing we found, not that there was any doubt about it, but it's one of the most direct demonstrations of Darwinian adaptation by natural selection you can imagine. Yes, they're getting to be better competitors over time. It's a common observation in other evolution experiments that evolution in a new environment gets off to a rip-roaring start and then tends to slow down over time.
Oh, whoops. Turns out when you try to prove evolution, you end up finding out why it won't work. Did you notice that? When scientists try to evolve organisms, it seems to run into the exact same issue that the genetic algorithms do. It converges on a solution, and evolution stalls out without new innovations. Don't worry though, that won't stop scientists from believing the theory is true anyway. Why? Because evolution is an ideology, not a theory, and it helps that that's where the money is. In this sense, genetic algorithms are a good analog to evolution. They show that evolution is capable of simple optimizations that eventually lead to convergence, where diversity is reduced and innovations stop. So evolution has very hard limits on how far it can go. In fact, yours truly made a video detailing this exact issue already, because it should have been obvious that this would happen, at least once you understand what it is evolution is proposed to do. See the link to the video in the description. Okay, so the first two issues aren't looking good for the theory, but what about the third issue, which is open-ended evolution? Well, first, what is open-ended evolution? Open-ended evolution is the idea of an evolving system which is continuously generating new innovations in a complex space. Open-ended evolution is more akin to what is proposed to happen in biology. That is, things constantly shifting and changing and evolving to meet the challenges of their environment, without end. This is precisely what genetic algorithms don't do, since they will stall out and converge on a single solution. The reason genetic algorithms don't do this is the same reason evolution probably doesn't do this either. The engine of biological change, mutation and selection, just isn't powerful enough to do open-ended evolution. But how do we know this? Well, because when we create genetic algorithms, we have to constrain the complexity of their search space or they will fail. It's called combinatorial explosion. And this just means that the number of all possible permutations of the system becomes so big that you will fail to find anything in it by randomly searching. Imagine creating an algorithm that shuffles words around in a sentence until it finds jokes. In order to make this reasonable, you'd first have to limit the number of words because some words just have little inherent comedic value, like rheometer. You'd also have to limit the size of that sentence because the complexity grows exponentially for every word you add to the sentence. So no matter how difficult that problem is, imagine now having to find that sentence by changing individual letters instead of words. You just increase the complexity by a number so big that it doesn't fit in the universe. No computer and no biological system has the computing power necessary to make changes on that sort of scale. But you need to be able to make changes on that sort of scale or you won't continuously find novel innovations. Think of it as a trade-off. The simpler you make the problem, the more likely you are to successfully optimize it, but the more likely you are to converge and cease evolving. However, if you make the problem more complex, you're less likely to converge, but also you won't be able to successfully optimize. And so genetic algorithms are a great analogy for explaining why evolution simply won't happen, for these and for other reasons. All that said, genetic algorithms are, in a way, a good analogy for evolution. Sometimes mutation and selection can operate on problems that are simple and where convergence isn't an issue. For instance, if you need to tweak a suboptimal protein, then just like a genetic algorithm, you can optimize it as long as the complexity is minimal and the front-loaded information is already there. This is how we get things like nylonase or certain antibiotic resistances in bacteria. But solving these sorts of simple problems doesn't change the fact that open-ended evolution, which is the kind needed to turn a raccoon into a whale, just isn't going to happen. Ask yourself this. They've been evolving E. coli for tens of thousands of generations, which would be the equivalent of millions of years for a species like us, and they still just have E. coli. Why, even in tens of thousands of generations, did the bacteria remain essentially stable? Why didn't it evolve? Even Lenski's best example of evolution in his E. coli experiment was when the E. coli evolved the ability to eat citrate. The problem is E. coli already has the ability to metabolize citrates, so this wasn't meaningful open-ended evolution. Why can't we successfully model evolution? Why can't we observe it? And why does it seem to violate all reasonable probability? It's because the theory is a farce, and there's no good reason to think it's true.